Hello, everybody, and thank you again for participating in this competition, especially on the machine learning one, which is quite important to us and to me. So here I would like to talk about three different topics. So first I will explain very quickly how the quant team is set up in APAC, especially on the equity derivatives part. As you can imagine, with all the sort of quants that exist at UBS that Mine mentioned, there are dozens of quants based in Asia. On the equity derivatives part, globally, UBS has around maybe 30 people, and there is a team of 10 is based in APAC, mostly spread across Shanghai and Hong Kong. Our focus is on models and technology for derivatives pricing, and especially here we have also quite a strong focus on stochastic volatility modeling. You will understand why it's important for some of the derivatives products that Vinay alluded to. Actually, stochastic volatility modeling, we got awarded our team in Asia Quant House of the Year in 2018 and 2020 for projects that relates to it. Actually, if you look on the internet on Risk Magazine, you will see that the 2020 project is quite related to the competition you are working on at the moment, if you have not seen already. Second component that I wanted to talk to is derivatives pricing, just so that you get a bit of context about how we got to the non-parametric modeling that we asked you to think about. So derivative pricing, I think you can decompose it roughly into two classes, the payoffs that we classify as terminal payoff. For example, the typical European options, vanilla calls and put options. It gives the right to the buyer to buy or sell a stock at a predefined time that people call expiry, let's say in 1 year, at a level that is decided today. And you can see from the definition of this payoff is that the payoff depends only on the value of the stock in 1 year. So you can imagine that models that are required to price such payoffs, they just need to get right the probability distribution of the stock in 1 year. It does not depend at all how the stock achieved its value in 1 year. What matters is what is its value in 1 year. The stock could have gone up, always down. What matters is what is the value at expiry. And then there is a more complex class of payoff that we call path-dependent payoff, as opposed to terminal payoff. And here there are payoff where it's not only the value of the stock at a given point in time that matters, both for the payoff and therefore for the price of the product. It depends on various features of the trajectory of the stock price. A simple one can be an Asian call or put option. So instead of having the right to buy or sell the stock at a given value in 1 year, it will be at a value that depends on the average value of the spot from now until 1 year. So you can see it does not depend so much whether it's going up or down, but the average value of the stock matters. So it's not only at expiry that the stock price matters here. And then you have also payoff where it's the direction of the move of the stock during its life that matters. A simple one can be a daily discrete barrier options. You can imagine that you have a level that is called the barrier, and then you will get something in 1 year only if the stock never crossed that barrier. For example, if you have an up barrier, then you can say, okay, you will get something in 1 year only if the stock remain below that barrier every day. And then you can see that this payoff suddenly becomes dependent on what the spot is equal to every day, and the models that are required to price this, the basic stuff that you need to ask for them is that the probability of the stock at every time horizon between now and expiry is consistent with how the market views it today. So the simplest model for that is called the local volatility model. It has been introduced by Dupier many years ago. It's a model that will be consistent with the stock distribution for every point in time from now until the expiry of the trade. But you can also see in the examples that I said that it also depends on future conditional distribution of the spot. For example, you can imagine easily that this product depends on what is the probability that the spot is going to be above the barrier tomorrow, given it was below the barrier today, for example. And this is a more complex class of probability distribution that you want the model to be flexible on, and the local volatility model does not have enough flexibility to allow you to play on this kind of distributions. So this is where more complex model like stochastic volatility model enter into play, because with these models, not only you can be consistent with what we call the terminal distribution of the underlyings, but also the conditional future distribution of the underlyings. And you can make them, you can set up the, let's say, the volatility of the volatility in this model, the correlation between the spot and the volatility, such that you fit a given market of complex payoffs. You can also imagine that if the payoff has a very long dated expiry, you are not sure what the rates will be when you want to discount the premium, or if the payoff depends directly on the rate, so it could also be depending on the stochastic rates models. So in banks, like most banks, they have the GPR local volatility model implemented, used for risk management in their production system. Most banks are like that. Where there is a bit less banks that are able to do it is with a stochastic volatility model. They are much lower model. It's not always easy to implement them for risk management in risk management system. And even when they are implemented and used, there is still the quoting problem of structured product. As Vinay was saying, the example of a client based in Japan who wants to do structured product, we have thousands of quotes like that, quote requests that comes to UBS every day, and we need to answer quickly the clients with a price. And while you could afford to risk manage your derivatives product, i.e. the product that you have really traded with some clients using a stochastic volatility model or stochastic rate model, jump model, any kind of model, in quoting, it's a much more complex problem because you need to be very fast. And here what banks tend to do is they quote in a local volatility model, and then they charge a fixed premium on top of their local volatility price to account for the fact that they know that the local volatility model could underprice some of the structured products they are quoting. And this way they are fast enough, and still they try to be conservative, acknowledging the limitation of the local volatility model. So this is good for speed, but you can imagine that because it can be a fixed charge that is not completely tailored to the market situation and to the product configuration, sometimes this fixed charge can be too expensive, in which case maybe you are missing some trade because you are charging too much to the client to do this trade, or too cheap, in which case maybe you do a lot of trade, but actually you end up losing money risk managing this product because you have not brought with you enough money to pay for the risk management of the product on your side. So ideal situation will be to quote using directly these complex models, but if they are too slow, or if other market participants don't do the same thing, you will appear as someone that quote very slow. Even if you quote accurate, you quote too slow, and you might end up losing some trades also by being too slow versus other banks. So what we have been trying to do is, can we achieve a very good quoting speed with complex models? And to do that, we asked ourselves the question, can we build non-parametric models, so machine learning kind of models that can instantly give you the price of the complex model given a market data situation and a payoff that you are trying to price? So this, if you think about it, is extremely complex. It depends on many, many factors. And we quickly eliminated that idea to a much more realistic one, which is trying to build a model that will learn the difference between a base model, let's say the local volatility model that already takes into account a lot of factors in its value, and the more complex model. The difference between the two intuitively should depend on much less factor, and it's much more realistic to train a model on it. So that's basically the competition that we organized here. We created a lot of market data scenarios and for each market data scenario, a lot of possible configuration of contractual inputs for a complex structured product. And then so this becomes basically your big matrix X in a typical machine learning product with all the possible features. And then the target is the true difference that we computed using the true local volatility model and the true more complex model that we want to use here. And this difference between the target that we want to learn using a machine learning model. Then at quoting time, what happens is that you would quote using the local volatility model, and then you call your machine learning model that in a fraction of a second is supposed to give you what is the actual charge that you want to add for this market data and this contract to get the fully embedded price that can take into account various effects, jump, stochastic rate, stochastic volatility, any kind of things basically. So that's how this competition is based on basically. And one, I think of the questions that you might have asked yourself that maybe is more obvious now. I think you might wonder why for this kind of model we are not just interested in the root mean square of error like in typical approximation of models. We are also very much interested in the maximum absolute error, because if we have a model that is okay most of the time, but in some cases can return completely crazy prices, that's also very bad. If the crazy price is way too expensive, very rarely, okay, maybe very rarely we might end up losing some trade. If it's actually way too cheap, it's quite dangerous for us because we will lose money on risk management. So that's also why the maximum absolute error was also very important for this kind of model. So it's quite an innovation, I think, in the quant space. I think all of us across banks, we are at the very beginning of seeing how to incorporate machine learning into pricing. It's a very complex problem. We have found a solution for it. Actually, the competition is trying to see if you have other ideas than us to build this model. Maybe you will find a better model, give us ideas. So this competition is very important for us because depending on the outcome can really be something that will help UBS as a whole. Like if you find a very good algorithm that is actually better than our algorithm, that's all the best for us as well.
So yeah, Alex, yeah, if I just you just mentioned just to sum up as well. You mentioned I mean UBS cared about overvalue or undervalue the quotation, so that's why you really care the most is about maximum absolute error, right?
Yes, correct.
Yes. Okay.
Because you want to be accurate in quoting, basically. It's not a problem. It's a problem where I want to know if I get a price, I know that it is off by max X bips, for example, and not that there is a 1% probability that it's off by 10%.
Okay. We have one question as well from people on YouTube is why is a stochastic volatility model slower than a local vol?
So very roughly, and we can enter into the details, but you can imagine that when you compute a structured product, you basically compute Monte Carlo methods for it. So you simulate spot trajectories. In a stochastic volatility model, you also need to simulate the volatility of each stock. Not just the stock, but also the volatility of each stock. So you can imagine, roughly speaking, that it should be twice slower than a non-stochastic volatility model. Actually, you can enter in the details. The pure local vol model is somehow a stochastic volatility model because the volatility depends on the stock level, but a true stochastic volatility model, let's say, depends on an extra factor than the spot level, and you need to simulate that extra factor. So you have twice the number of things to simulate in a stochastic vol model, roughly speaking.
Okay, and I think as well, accumulator as well as path dependent, so you are usually...
Yes, so accumulator is also another kind of path-dependent product where there will be indeed a stochastic volatility effect on top of a local volatility, various effects as well.
Okay, okay.
I don't know if there is any other questions on this competition or this particular topic, or even some more broad question about the equity derivatives quants?
So what are the structured products were really, you are based in Hong Kong. What are the structured products are really popular, in Asia Pacific in general? And
because there is definitely the accumulators, as you said, there is
Europe as well. Sorry, and if the market, is it different from Europe or US? Is it?
But there is accumulators a bit in each market. We have also a very huge class of products that is called autocallables. They are very complex barrier-based product with multiple levels of monitoring, multiple barriers. They are also in each regions. Maybe in the US, what people would have more compared to a region like Europe is autocallable on stocks versus as opposed to autocallable on indices. Maybe that's the underlyings that are a bit different depending on the market. Maybe shorter expiries in the US sometimes than in Europe or APAC. But this kind of products, they exist in all markets. So this kind of competition is useful globally to UBS, and this kind of topic is useful globally to UBS because the logic applied here can be reused in many payoffs and many kind of underlying. That's also what makes it difficult, is that the market data features that you need to engineer, they need to work for almost any kind of underlyings that people might want to trade.
So we have another question as well is, how does machine learning improve risk management? Because, okay, you are talking about the this machine learning using for quotation. So I guess the participant would like to know, probably, are you using it as well in risk management? And
so machine learning for risk management, it's let's say another step. For example, for quoting, what you care about is the price. For risk management, you care about the Greeks, so the sensitivity of the price with respect to various market observable, for example, the volatility, the spot. So you could imagine that if you have a good enough machine learning model, it can tell you what should be the price when you bump the volatility up and down to compute your vega, and then you compute the difference. A typical finite difference algorithm will give you the delta. That said, in that case, it will be a more complex problem for people to solve because you want the price returned by the ML model to be smooth with respect to every feature that goes in the model. Otherwise, if it's not smooth and the price can jump with a small perturbation of an input, then you will get extremely noisy Greeks, and it's completely unusable for risk management. So that's one additional component to take into account. For this competition, we didn't want to create something so complex, and we were just focusing on the pricing aspect of it. Also, for risk management is a bit less of a concern for quoting because you don't have to reply within a few seconds to a client with a quote. Like you have your huge farm of computers that compute the risk, and within a few minutes or hours, depending on the risk, and you get your results. So the time constraint is a bit less critical than on quoting.
Okay, thanks, Alex. Maybe 1 minute to conclude. After that, I'm going to pass to Vinay to conclude the webinar. Sure. If you maybe want to say something to the students and for this competition, I don't know if you have.
Yeah. So for this one, as I said, this one we designed the topic to be very useful for us and of practical use. As I said, I wouldn't be surprised that one of the students' team or many teams, like who knows now a lot on machine learning through their studies, might have a different view than us and produce a model that competes with ours, might be even better. We might learn from it, and we might use the ideas later. So that's why this topic is, I find it very good for us because there is really a practical use after that. We can learn from it basically and can be used afterwards.
Okay, yeah. Thanks. And even if we have 350 teams registered for the competition and 250 teams registered for this specific competition. So
okay.
Hopefully we'll get some.
Yeah, hopefully.
Yeah. So
your turn.
Sorry. Thanks, Philip. Thanks, Alex. So the one thing that we really want to emphasize is this again. These are some of the kind of projects that's actually going on as a quant thing, and as I said, UBS on its own is actually trying to become as quantitative and digital as possible. So one request for all the participants here is please go and register yourself on the link there, the link on the Alphien platform. And there's also an email that was sent through Alphien. That will really allow us to talk to you and try to have a conversation about what kind of careers as well that you would be interested, and this especially in banks. What can you be doing? What kind of interest that you have? How can we align that? So that is really, it's not just about, it's also the competition, which is really the key part, but it's also how we can actually help you otherwise as well in building your careers.
Yeah, we have a question on this, Vinay. What are the key things you are looking for when hiring a quant?
Okay, I was going to joke something, but I'm not going to do that. So I think the key things that it's the ability to, as most of the quants, it's not going to be, you don't get a question and you go and solve it directly. It's just like the problem that Alex was mentioning, that, okay, you can do everything with the black shows plus this and that and everything, but there's always a better solution. How do you think outside? How do you actually try to make a problem, simplify the problem, and how do you actually solve it? How do you, that's the area that the skill set that you're looking at. So usually it's a good mathematical background and a good technical skill set, and the ability to think outside of the general, I'm not going to say think out of the box, but think in a bigger way, and how we can actually impact your projects is the main thing that we really look at.
Thanks, Vinay. So I think we're going to close this webinar. Thank you very much for your participation. And I hope the best of the student. I hope they learn a lot for doing this webinar. Thanks to both of you.
Thank you very much.
Thanks.
Thank you. I think there's a lot happening, so definitely encourage people to register and also to reach out to us if there's any questions. There's a lot to learn here. Thank you.
Okay. Thanks, Vinay. Thanks, Alex.
Thank you. Bye-bye.